and we will talk about algebraic algorithms. Up until now we saw how to use inclusion exclusion. Today I will give you another algorithm for matrix multiplications. Okay? And our parameters still will be slightly non-conventional. This is also known, this whenever you use this n kind of parameter, like n being number of vertices or number of edges or number of variables in a formula, okay, then all these things are slightly non-conventional, and this is also termed as exact exponential time algorithms. And these have been around for more time, like from 70s and other. So, today we are going to talk about an algorithms based on matrix multiplication, and this slide is from quite early slide by Lucas, but yeah, so I will use that. Okay. So, we are going to talk about square matrix multiplication. So, you are given two matrices n cross n, A and B, and you want to compute the matrix C A cross V. So, that is very simple. The classical algorithm takes NQ time, because all you have to do is that you are given A and B. So, you are given A and n times n matrix, and B another n times n matrix, and all you are interested is in A times B. So, what do you do? So, what is the first entry? Basically, first entry is you look at the first row of A, multiply it with the first column. So, this entry will get multiplied with this entry gets multiplied with this entry gets multiplied with third entry, so on and so forth. So, to get one entry here, you need basically it is a dot product, if you think of a dot product. So, if this is, say, let us call this row 1 to row n for this one, and let us call this column 1 to column n. So, what is the first one? Is basically a dot product of R 1 C 1, and what is the second entry? Is basically dot product of R 1 dot C 2 dot product of R 1 dot C n, and second is R 2 C n, R 2 C 2, R 3 C, sorry, R 2 C 2, R 2 C n dot 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 R n C n, R n C 1 C 2, R n C, right. Now, so A cross B also has n square entries, okay, and each dot product is nothing but n multiplication. So, overall in n cube time you should be able to do this. So, this is basically what is Cij is like Aik Bkj, this is basically. So, you have total number of n cube arithmetic operations. So, you can do square matrix multiplication in n cube arithmetic operation. Okay. So, this is just a classical algorithm. Okay. And but there are also, so there is a very simple divide and conquer algorithm. So, suppose you you take n equal to 2 power k without loss of generality. So, you divide A, B, C into blocks of size n by 2 cross n by 2 cross, this is n by 2 times n by 2, so on and so forth. And so, what is C 1? So, you take this, multiply with this, plus you take this and multiply with this, and so on and so forth. So, we get the recurrence that if you are trying to solve multiply n cross n matrix, then this is 8 1 2 3 4 8 t n of t plus order n squared, and hence t of n is order n cube, because the last level dominates, it has like roughly n cube nodes. Okay. So, how many multiplication we had? 1 2 3 4 5 6 7 8, and that is what corresponds to this 8. So, like 8 big multiplication of objects you will get, and from there you have just have to sum them up, right. So, once you have got this multiplication, then it is nothing but just normal summation, which is like order n square time. So, but what is the time consuming is that this 8 big matrix multiplication of matrices of size n by 2 times n by 2. Yes. But if you, I am sure you have seen this in your classical algorithm course also, this approach by Strassens. So, what is by approach by Strassens? He said, look, if we really want to get this, multiply this matrix A comma B, right, then we do not need to compute 8 matrix multiplication, but we could compute some 7 matrix multiplication, okay, 7 matrix multiplication, and then the product matrix C can be written as sum or addition of this product matrices. So, he came up with this very nice 7 matrix multiplications of size n by 2 times n by 2 times n by 2 times n by of the matrices of order n by 2 times n by 2, and then he was able to write, look at, for example, what is this term here? It is nothing but sum of m2 plus m4, so on and so forth. But now he has reduced the matrix multiplication to not from 8 to 7 matrix multiplication of matrices of order n by 2 each. So, that implies that T of n is 7 T n of by 2 plus order n square, and so the running time became n to the power 2.81. Okay. And let omega be the constant to multiply the best matrix multiplication. So, there is a trivial lower bound of omega at least 2, because you have to look at each entry of this matrices, and that is like n square entries. So, Copper, Smith and Wingred obtained that you can do using some non-trivial application. Okay. Omega is 2.376. Then Stothus obtained slightly improved bound, and in 2000 Williams got 2.3727. This is even more smaller currently, this is not current. So, this number is slightly better than what you see in the slides, but the moral of the story is that you can do matrix multiplication much better, like much closer to 2 than n cube. Okay. And now we will exploit this algorithmic development about matrix multiplication to design an algorithm. Okay. So, this is a standard exercise that you are given a directed or undirected n vertex graph G. You want to find a triangle in G if it exists, compute the number of triangles in G. All these are very standard exercise. Okay. One thing is trivial, right? You can NQ algorithm, right? Just try all possible triplets and do NQ time. But there are slightly better algorithm. Let A be the adjacency matrix of an n vertex graph G, directed or undirected, right? And you fix any k, then for every ij 1 to n, if you look at the kth power and look at, so basically what it says you, okay. So, what it says you that look at the adjacency matrix of a graph G. So, what is an adjacency matrix of graph G? A. So, you have right, and what is A ui uj is 1 if ui uj is an edge. Okay. Then you put 1 here, 0 otherwise. So, this is the adjacency matrix, and if you look at the power a to the power k, right, kth power of a, and you look at this ui uj or maybe or I comma j, then this is nothing but it counts number of walks of length k from ui to uj. Okay. Or you can also do dynamic programming for all that you can, but like this is what it can do, and you can prove this using induction because okay. 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 So, this is what it means, it is easy induction around k, but what is the corollary? What is the corollary? Can we find a triangle in G if it exists? If you go back here and look at A3 and look at the diagonal entries. Okay. So, diagonal entries are what? Those are those walks which, suppose this is like say 3, it starts at 3, it goes somewhere and it has to come back, right, and it is a length 3 walk. So, if it is a length 3 walk, suppose I start at vertex 3, I go somewhere. Okay. So, what will it can consist of? I can go here, but notice if I come back to 3, right, if I come back to 3, then it cannot be an walk, and then if I look at, so all the closed walk of length 3, which I think this is not a good, Okay, so look at a vertex I and look at a walk of length 3. So I start at I go at j some other vertex, because in the first, right, because there are no self loops. But now where can I go, right? I can either come back to I, but then if I go out, that's not a walk which starts at I and ends. So what are we looking for? We are looking for A3 I comma I, like those walks which starts at I, ends at I. Okay. So basically what happens at A3 I comma I is that it's basically I start at I visit some other vertex j, okay, I have to visit some other vertex k, and then I come back. But then this is a triangle. Okay. So then this is a triangle, right? So basically graph as a triangle if and only if in a to the power 3, like the third power of a, has non-zero entry. And in fact what it is, so basically if you wanted to count the number of triangles, then you can count all the, you can sum the trace, right, then you can sum the trace, right, and then you know that, like, and then you have to divide by some number like 3 factorial, because you will be counting the same cycles several times. So you just you sum this up and divide appropriately. So in n to the power omega time, we can find a triangle in G if it exists. We can compute the number of triangles in G if it, like, right. So we can do this task in n to the power omega time. Okay. So the problem we are interested in is the following. Okay. So you are given a 2 CNF formula, so with n variables, and we want to find an assignment which maximizes the number of satisfied clauses. So remember, it's a 2 set formula in the sense that you have n variables, and each clause consists of just 2 variables, x1 or x2, x3 or x2, x2 or x not x5, so on and so forth. So what is CNF? It is ANDs of, it is an ANDs of ORs. And what is a, right, what is a satisfying assignment? What is an, so you want to find a function from say v1 to vn if you have n variables, let's, okay, say x1 to xn, to 0 1, and when a clause is satisfied if, so for example x1 not x2, so x1 if assigned 1, then this clause is satisfied. So if any one of the literals is set to 1, then the clause is satisfied. Okay, or you have, if you set x2 equal to 0, then not of x2 is 1, so this clause is satisfied. So you want to find an assignment which satisfies the maximum number of clauses, and for 2 set formula you can check whether there is an assignment that satisfies all the clauses in polynomial time, but finding an assignment that satisfies maximum number of clauses is not easy. Okay. 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 So what are we interested in? The decision version of the problem is that phi with n variables and a number k, and we are interested in, is there an assignment which satisfies exactly k clauses? Okay. And because if you wanted to find the maximum number of satisfying assignment, then you can start from 1, 2, 3, 4, and you can go up to the maximum. Since the number of clauses are like n square, what it means up to a clause factor in the sense that no clauses are repeated, for example. Okay. So is there an assignment which satisfies exactly clauses? Of course, max 2 set is NP complete, so naive algorithm will definitely work in order 2 power n time. What? You try all possible assignments of x1, right? So anyway, how many such number of functions are there, right? So such number of functions are actually at most 2 to the power n number of assignments are there, right? Each xi could take 0 and 1, so the total number of assignments is 2 power n. Okay. So the very naive question was that, is it possible to design an algorithm which is better than 2 power n? Can we come up with an algorithm with running time say 1.9 to the power n? And William came up with some very beautiful algorithm, okay, and he used in this like he constructed an auxiliary graph, and for that he used matrix multiplication. So, what he did is the following. So, before we, let me give you an overview of his algorithm and then we will see. Okay. So, what he did is the following. So, suppose you had this x1, x2, xn. Okay. So, he first partitions this into v0, v1, v2, partition as equal as possible. Okay. So, suppose if n would have been say some 3k, then v0, v1, v2 are not 3k, let us not use, because that is like number of 3l. Then v0, v1 and v2 will be of equal size and l. Otherwise, you can always come up with a sets which are like roughly like 1 or 2 elements here and there. Okay. So, you come up with this partition. Now, what is his idea? His idea is that look at this v0, v1 and v2. v0 is like, say suppose v0 consists of x1, x2, xn by 3 variables. v1 consists of xn by 3 plus 1, x2n by 3 variables. Okay. And v2 consists of x2n by 3 plus 1, xn variable. So, he says that, okay, let us enumerate all the assignments of v0. So, what are the possible assignments of v0? x1 can take 0, 1, x2 could take 0, 1, xn by 3 could take 0, 1. Okay. So, enumerate all assignment of v0. How many of them will be there? 2 to the power n by 3. Enumerate all assignments of v1. How many of them are there? 2 to the power n by 3. Enumerate all assignments of v2. How many of them are there? 2 to the power. So, in total we have enumerated how many assignments? 3 to the power 2 to the power n over 3. And now, each of these assignments are going to form like each assignment will correspond to a vertex in our graph. Okay. So, total number of vertices in our graph will be 3 into 2 to the power n by 3, and this is what is happening. So, you fix an arbitrary partition v0, v1 into 3 equal parts, and what is a vertex? It is a set of all possible assignments vi from vi to 0, 1 for I equal to 0, 1, 2. Now, how do you give an edge? Okay. So, giving an edge is very simple. So, you put an edge between every assignment. So, now if you look at this, let me, okay. So, this is, let us say, okay, assignments corresponding to v0. This is assignment corresponding to v1, and this is assignment corresponding to v1, v2. Okay. So, you have vertices for. Okay. And basically, these are like vertices, right? These are vertices. So, there are 2 power n over 3 of them, 2 power n over 3 of them, 2 power n over 3 of them. And now, what I do? You make a complete bipartite graph, right? So, for every vertex u and v here, you put an edge. Okay. So, this is a complete bipartite graph. This is a complete bipartite graph. So, you give all the edges from here to here, here to here, and here to here. Okay. Right. So, you ask yourself how many edges are here. So, there are 2 power n by 3 vertices, there are 2 power n by 3 vertices, all possible edges. So, this is like 2 power 2 n by 3. Okay, fine. How many edges are between v1 and v2? Another 2 power n by 3. Very good. Between v2 and v0, how many? Another 2 to n by 3. So, you have roughly 3 times 2, but still this is strictly less than 2n number of vertices, number of edges. This is strictly less than 2 power n number of edges in our graph. So, this is how you make your graph. Okay, so this is how you make. So you have all the assignment corresponding to V0, all the assignment corresponding to V1, all the assignment corresponding to V2, and you make a complete bipartite graph between V0, V1, V1, V2, V2, V3. Okay. Now, in this graph, we would like to compute a triangle and say, hey, we are great. But to do that, our goal was to check if there is a triangle. So now the idea of the solution is that we assign weights to edges so that the weight of the WAV triangle in G equals the number of clauses satisfy the assignment VWU. What I mean by this? Now, if you pick up a vertex here, let's pick up a vertex here. Let's pick up a vertex here. Let's pick up a vertex here, right? So if I take a partial assignment here, a partial assignment here, and a partial assignment here, then that corresponds to an assignment of all the variables, right? Now, right, that corresponds to assignment of all the variables, and I would like to assign edges to this particular triangle, because we know you take up this triangle that it is same as the number of clauses satisfied by these three variables, these concatenation of assignments. Okay. So this is what I would like to do, and then it is sufficient to check if there is a triangle of weight k in G or not. Okay, so we would like to do these two things. Okay, so remember, if I pick up a vertex here, pick up a vertex here, and I pick up a vertex here, then take this and this, then tells me number of assignments in G. That fixes an assignment of my variables, and that immediately tells me if once I fix number of clauses that they could satisfy. Okay. So far so good. So first let's solve the first problem. How should we assign weights? Let C be all the clauses satisfied under the possible assignment V, then the number of satisfies. Okay. So these are the some sets, right? Then the number of clauses satisfied under the assignment VWE amounts to, we have just seen inclusion exclusion. Okay. So like CB is all the clauses. So set CV, we are interested in this, but now maybe some clauses are satisfied both by V and W. So CV, CW, C1, right? You now subtract those clauses, and then because of inclusion exclusion, you have to also add CV intersection CW union CW. But imagine yourself that these are disjoint, right? So look at a clause which is also in the set CV. It means it is satisfied by some variable V, like some variable. It contains some variable W which is contained inside V0, and okay, I look at some set W, like some assignment W. It means this clause is satisfied by some variable which is in V1, and then it also belongs to CU. It means it is like, yeah, so this is another set of variables, right? So basically what it will mean, what I wish to say is this: look at V. V corresponds to a partial assignments of V0, W corresponds to partial assignment of V1, U corresponds to partial assignment on V2. Okay, and now fix a partial assignment, and they say, look at these are the clauses which are satisfied by partial assignment V. Okay, now let's fix a clause C that belongs to CV, CW, and C union. Okay, it means the clause C must contain a variable from V, right? C contains a variable from V0, C contains a variable from V1, C contains a variable from V2, but that cannot happen because it is a two set. So this contributes to 0. Okay, so this contributes to 0. Okay, so this is not at all an important factor for us. So for us, CV union CW is just this much. Then this is easy, right? Then there is a very easy assignment. Right? So CB, so you ask, and there are 3 edges. So for edge VW, you assign, like you fix V, so for you fix VW, edge VW, and you assign CV minus CV intersection CW. So basically, whichever is the largest index, you assign the value of that and you subtract. That's it. Okay. So so this is how you can. So you put the weight xy is Cx minus Cx intersection Cy. This is how you put it. Okay. So we can think of this as a, right. So now look at this triangle, right. So for an edge here, you like for an edge which starts at here, okay. So think of this way, that you will always give importance to V0. If you look at V1, you will look at an edge between V1 and V2. So for edge between V1, V0 and V1, okay, between, you will assign the intersection weight as well as the weight of this. For edges here, you will assign the intersection weight as well as weight, and for edges here, you will assign the weight of this vertex and the edge. So this is the convention you make and assign weight this. Okay. Now you know that if you, so what we have been able to achieve? So we are able to achieve that now if you look at any triangle in this Hughes graph, look at any triangle and look at the sum the weights of the edges, then that is exactly equal to the number of clauses satisfied by this. Now we do some pre-processing. What kind of pre-processing we do is as follows. We say, okay, fine. Look at, if I am looking for a weight exactly k, then let's look at this triangle. Maybe I want the triangle should look like weight k0 here, k1 here, k2 here, so that this is equal to k. How many such partitions are there? There are at most order k squared such partitions are there, because once you fix k0 and k1, k2 gets fixed, okay, because k is fixed. So for every partition, you build the graph G, K0, K1, K2, which consists only of what property? Edge of weight K0 between this. So now I say, look, I am only interested in finding a triangle contains edge weight K0 between V0 and V1, weight of edge between V1 and V2 is K1, and weight of an edge between a vertex in V2 and V0 is K. So what you do? You look at your big graph. Okay, you look at your big graph, and from here you delete all the edges whose value is not equal to k0. You delete all the edges from here whose value is not equal to k1. You delete all the edges from this. So now what you know? Now the property is that then it suffices to check whether there is a triangle at all, because if there is a triangle in our graph, then the way we have any triangle must contain an edge, because it's a tripartite graph. Any triangle must contain a vertex from V0, V1 and V2, right? And then it must contain an edge of weight K0, must contain an edge of weight K1, must contain an edge of weight K2. So if you sum them up, then this is going to be equal to K. So now what is our algorithm? So in this graph, G, K0, K1, K2 graph, we need to check whether there is a triangle or not. So we have an algorithm, right? We saw an algorithm to test whether we have a triangle or not in time n to the power omega, okay, where n is a number of vertices. So in our graph, how many vertices are there? So the number of vertices are there is right. So the running time of our algorithm will be this. So this is equal to, if you notice, 3 to the power, of course there is some big O here, okay, 2 to the power n omega divided by 3, right. Now we know that omega is less than, strictly less than 3. In fact, omega is like roughly like 2.3 or something, 3, let's say. Say 3.7, okay. Okay. is 3, 7, right. So, now till omega is a constant, n, this is less than, strictly less than n, right. So, yeah, so the running time of this, but we also had to construct our graph. So, to construct our graph, how much running time it takes? It takes running time, we had 3 times 2 n over 3 vertices, and then you have to give an edges. So, the total number of edges were 3 times 2, 2n by 3, right. So, this is some big O of this is an extra cost of constructing this graph. Of course, you also will have some polynomial factor to take care of k, but the whole total running time actually boils down to constructing this graph and then running this polynomial matrix multiplication algorithm on this. And since this can be done very efficiently, as we have seen, right. So, this would have been a better than 2 power n algorithm for if we had a matrix multiplication algorithm as close to anything which is better than 3, 7. So, if we can get an algorithm with running time, say for example, for matrix multiplication which is of n square time, then this algorithm will run in time 2 to the power 2n by 3, right. But currently, it is a matrix multiplication running time which dominates this algorithm. Okay. Okay. So, yeah, so given all this has these many vertices, we can verify contains a triangle in this on time or not in this much running time, right, and this much space, because you also have to take a big graph, and hence we can check whether G contains a triangle of weight k in time k squared 2 to the power 2 omega n by 3, because you have to take about all possible values of k. So, in this much running time, we can actually check whether like find the maximum number of satisfying assignment. Okay. So, what we learned that there is an algorithm for max 2 sat running in this much time and this much space. In fact, you can also count the number of this, and here is an exercise which I would like to give to you. Okay. Starting from here, there are some exercises that you could try. Design an algorithm for max cut running in time 2 minus epsilon to the power n to the power big of 1. That is the first algorithm, okay, exercise. So, you have to design such an algorithm for max cut, right. So, what is the max cut? You want to find the partition of vertex set of graph. So, the number of edges going across is maximized, okay, is maximized. Okay. So, definitely there is a 2 power n algorithm, right. You try all possible partition and do this. This is one exercise. Exercise 2, design an algorithm for bisection, let us call it min bisection in time. So, what is a min bisection? So, you want to find a partition of vertex set again Vg into 2 almost equal parts, right. So, the partitions, say suppose this is V1 and V2, cardinality of V1, V2 should be at most. So, they should be differ by at most 1, and number of edges that go across are minimized. Okay. There are several other applications of matrix multiplication, but these were the simpler application that I would wanted to share with you, explain to you, and yeah. So, that will be it for on matrix multiplication. Thank you.